Takže teraz bude nasledovať prednáška s názvom Fast, Faster, Fastest, Object Storage, Cloudbox Storage and SSD, ktorého speakerom teda bude László Madarász, ktorý je špecialistom v UI engineering odbore a zastupuje tú firmu Altinity. So stage is yours.
Okay, thank you for the introduction and welcome everyone. I'm very excited to be here. My name is László Madarász and today's topic is going to be about cloud storage performance. And before we get into that, I would like to ask to raise your hand if you work with any form of cloud storage. Okay, that's quite a lot then. This is probably going to be interesting for you. And I think it's also in the title that we're going to look at analytic databases, which is a pretty specific topic, but I think what we found can be interesting for everyone here. So first, let me introduce myself quickly. I am a UI engineer at Altinity, and this presentation was put together with the original mastermind, Robert Hodges, who is the CEO of Altinity. And Altinity provides enterprise services for companies who use ClickHouse. And ClickHouse is a magnificent analytic database. I will tell you a few words about that a bit later. Sorry, just a moment. I just want to make this a bit larger. Yes, thank you. So you can see a few of the main questions that we are going to have today. First, I'm going to introduce three main forms of storage that we can encounter in the cloud. And I want to say that I'm going to bring examples from Amazon. So the product names that I'm going to use are going to be from Amazon. But if you use any other major storage provider, you probably encounter the same kind of storage system, just under different names. And I'm also going to talk a bit about how we can measure performance, because it's really tricky, especially with databases. It has a lot of factors. I'm going to say a few words about what an analytic database is, and then we go into the main topic, which is how storage affects analytic database performance. So first, let's go into how these storage types work. So first, what we're going to look at is the NVMe SSD. How many of you have heard about this, just so I know who I'm talking to? Okay. So basically how an NVMe SSD works is that it is physically connected to the host machine. And whenever you rent like a host, you usually don't rent the whole physical machine, but you only rent the virtual machine. And the trick here is that although it seems logical that you can only use part of the SSD when you rent a part of a machine, which can be surprising is that whenever you have a throughput, like whenever you have a bandwidth there, you can also get part of that bandwidth because it is related to the virtual CPUs that you use. And the reason is that NVMe is a technology where, like compared to the older standard like SATA, SSD is directly connected to the CPU, and this allows for great bandwidth, but also directly correlates with CPU performance. So here you can see a few tests that we have done. The way we did this test is that we wrote a small program, and we just told it that it should write the same file 50 times, and we just looked at the results. And this file was about half a gigabyte. So if you look at the left, those are the write performance data. And what is interesting about is that the times that it took to write these files are scattered around, and then everything just gets into line, and also it gets lower, like this, the speed seems to increase. So the first question is, what causes this like instability in the beginning? And the answer is that we couldn't figure out. Our guess is that it's probably because it's in the cloud. There could be a lot of factors, for example, network problems or any problems that the provider currently had. Yes, the interesting thing is that it only happens with NVMe SSD, so none of the other storage methods will produce this. But after that, for about the last third, we can see that the write performance just goes up, like it takes very little time to write a file. And our idea here is that probably a write cache starts to work here. Because one important thing that I didn't mention here, that whenever we use an NVMe, we can also use the operating system's cache, which helps us both with writing and reading data. And we will see later that this is not true for all of the storage methods. So when we look at reading, we can also see this caching effect. Like for when we read the files for the first time, it takes more than 1 second for each file, and then it gets to about the half of this time when we only read from the cache. And as I mentioned, the performance or the bandwidth correlates with the CPU size. So on this graph here, this might be a bit difficult to interpret at first, because here we measure the write duration and also we order them by the amount. So what you can see here is like around 0 we see the fastest write speeds, and around 100 the slowest write speeds for both virtual machines. And the one in the blue, as you can see, is 4 times like a 4 times stronger machine than the one marked with red. And what you can see is that, like, around the edges, they have similar performance. But when we go to the main part, the most usual result, the one with the larger performance, basically it performs almost exactly 4 times faster. So this is what we would expect, because we have a 4 times faster CPU here. Okay, so let's move on to the next form of storage, which is the block storage. So the difference here is that the block storage is connected over a network, and the machine doesn't really know about this network, doesn't know how it works. It just sees the whole network as hard disk, basically. And what is similar to the NVMe, that we can also use the operating system cache here, so we also have this advantage here. When we look at the performance, what we can see is that it is mostly slightly slower than an NVMe. It has some differences. As I said, we don't see this kind of instability that we had before, but we see the same like buffer or cache effect. Like when writing, we can see that this buffer gets saturated, and then we get slower writing times. And when reading, we see the exact opposite. Like first it reads, like every read takes almost 4 seconds, and then it actually performs better than the NVMe when it reads from the cache. Again, like these are measurements that we took for ourselves, so we cannot explain everything exactly. Like maybe Amazon knows the reason why these work like this. We just wanted to see if we put them among certain circumstances, how they will perform. Okay, so our last type of storage is S3 object storage, which is a completely different story, like a completely different way of working with storage. It works a lot like an API, like you can just basically put requests to create or get files. but you cannot modify them when they are already created. You cannot just modify a part of a file. And also what you cannot do is you cannot use the operating system cache. And as you can see here, all of these graphs are linear, like there is no sudden change in the performance. But still, when writing, it performs similar to the block storage. And when reading, it actually gives a pretty good performance when we don't consider the cache. So if we would test all storage types without a cache, this would be a pretty good result. But if you compare it to the cache result, it's inferior to the other storage methods. So here's a comparison of all three methods. And this only takes reading times for consideration. And what you can see here is that like S3 is the slowest of them all. Like it takes it the most time to read. But also for, like, this is again a percentage, so we can take a look at like the fastest and the slowest like read commands or like read executions. And you can also see that if you talk about block storage, we also get some pretty slow results. That's probably when the cache like couldn't fire up yet. And the NVMe is like constantly performing at a good rate. Okay, so what now we are going to do is we take a real use case, like we try to run a database on all of these storage types and see how it performs. Because what is going to be interesting is that even if we have these storage types and these storage type results, running a database is a completely different thing. So I would like to introduce ClickHouse. As I said, we at Altinity provide support for ClickHouse, which is an analytic database that runs like any other SQL database. It can run on any environment. It runs on my laptop. It can run on the cloud. And what it excels at is dealing with like huge amounts of data. And when I say huge, I mean like hundreds of billions or even trillions of rows, which is, if you take a MySQL database, it would probably collapse, or like it would take a lot of time to fetch data from a database of this size. And the way it can work is that it stores data in columns. So whenever we make a query, we don't have to read all of the columns. It only reads the columns that we actually need. It also has very good compression. It utilizes something that's called the shared nothing architecture, which means that every node, like it can be distributed to different nodes, and every node has its own computing function and storage function, and there is no overlap. So this enables us to run queries in parallel. So we just run one query, and all of the nodes can do this simultaneously on multiple threads, which gives a huge advantage in processing all of this data. And also, it is open source. So, as we are on a Kubernetes conference, one of the reasons that we brought this topic is because we run this whole thing on Kubernetes. Like Robert, who actually created this presentation, he has been working with databases for over 30 years, and he told me that when he first encountered ClickHouse, it was actually a real challenge to set it up. Like it requires a very complicated infrastructure, like multiple nodes connected. And Kubernetes makes it really simple for us to, it actually takes about a minute to bring up a whole ClickHouse cluster using Kubernetes. And as you can see, there is like a rough outline how it looks in Kubernetes. Like we have a stateful set, which contains all of the pods which represent processes running on the hosts. And the other important part is like the first important part is the processes. The other important part is the storage that we use. And for this, we use persistent volume clays, which will turn into persistent volumes. And in this example, we put AWS EBS storage here, but it can be any storage that we'd like to use for that database. And Altinity developed an operator called Altinity ClickHouse Operator, which is responsible for setting up ClickHouse on Kubernetes. I think everyone here is probably familiar with how operators work because I've also heard it in the previous presentation. Yeah, basically our operator makes sure that the correct resources are created and maintaining them so that there will be no unexpected errors. If one of them goes down, we can start a new one, etc. And what I would like to show you is that, and this is going to be a bit tricky because I have this tiny screen here, how easy it is to set up a whole ClickHouse cluster. So this is about all of the code that we need to start a ClickHouse cluster in Kubernetes. And actually, this is more than that. Like we don't even need this part with the users. And if I'm correct, this one is for NVMe. Or no, sorry, this one is for EBS, and this one is for NVMe. And you probably see how little change there happened. And we could just simply switch to a completely different storage. And as I said, this is a really complex database system. Like enterprises use this to store like trillions of rows of data, and still, this is the only code that we need to run this in Kubernetes. So I think this is really, really amazing. And this is about what we described in this file. Like this is what it translates to. Like this, like on the left, you can see an instance with an NVMe SSD, and on the other side with block storage. So the way we tested is that there is a benchmark tool called ClickBench, which is specifically for analytic databases. Like it basically runs queries which are realistic queries, like ones that we would run in e-commerce. And it runs a bunch of them, about 40 something, and it runs them multiple times. So we can also see like the effect of like starting up, because of course when we start up the database, it's going to be a bit slower probably. It also checks caching. So the first test that we did here, and before I get into this, I need to say that we didn't even test S3 with these results, because from the previous test result, it was clear that it's not going to be the fastest, because it simply takes a lot of time to read from it. So the first test that we took were on NVMe, and the interesting thing here is that, like, you can see with blue the results that we did when caching was enabled, and the red one means that we disabled the operating system cache, and there is almost no difference between the two. So how can this happen? Like as you could see in the previous examples, cache improved performance a lot. So why doesn't it work like this here? The thing is that, and this is why it's really like it really makes a huge difference what kind of database and how you use it, that ClickHouse already minimizes input and output operations, and provides us with a lot of small tools that will speed up the whole process. So basically, it's a substitute for operating system cache. Also, you can, as I said earlier, you can read in parallel, which again speeds up the whole process and maybe even makes the operating system cache obsolete in this case. Also, one more thing that I didn't say here is that the queries provided by ClickBench are dominated by compute. So we probably do more computation here than I/O operations. That also counts, makes a difference in this case. But as you will see in the next example, it's not only about that. So for the next case, we did a test on the block storage, EBS. And what you can see here is that it's also pretty quick. It's not left behind compared to NVMe, although it should fall behind at least more significantly than this. There is an interesting spike there. I won't go into that now, but if someone doesn't know what to ask at the end, then I suggest this because I think this is really interesting. So what you could see here is that there's not a lot of difference, even though the storage types themselves provide different bandwidths. And this is what I just explained earlier, that ClickHouse provides all of these tools for caching and basically speeds up the whole process a lot. So this is the two results that we have seen, the last two results, and put next to each other. Both of them are cached. So the blue one is NVMe, the red one is the block storage. And the surprise here is that the block storage is actually not slower, but faster in all of those queries, which is the exact opposite of what we expected. So why is this? There's actually a little trick here. When we used the block storage, we used a different type of VM. And I think there are, most people will point out quickly what the difference is. We used a larger VM for the block storage. And even though the storage itself is supposed to have less bandwidth, still the CPU drowns this effect, and we will still get better performance with a larger CPU. So what is the conclusion here? It's actually just a few simple points that might be interesting for you if you think about what kind of virtual machine or other cloud service to order from Amazon or any other cloud provider. The first thing is that VM size affects not only computation but also I/O bandwidth. So if you use a larger VM, you will get more throughput. The other thing is that object storage doesn't use a cache. If you want to make it faster, you need to develop a cache yourself. Also, ClickHouse, and this is interesting for those of you who want to work with a huge amount of data and analyze it quickly. That ClickHouse tries to make all of these I/O operations small and small in number and small in size. Also, what I have already mentioned is that computation-intensive queries will drown the I/O effect. So again, you can have a lot of bandwidth, but still CPU can win this race. And the opposite of this, that if you use an i3 or any kind of small VM on Amazon, this might be the bottleneck on your storage access. And the final and probably most important thing is that databases are complicated, and not only databases, but all kinds of applications. So what we recommend is that each time you plan to plan an infrastructure, you should do your own tests that are specific to the use cases that you have. Because as you could see, whenever we switched the use case, we got completely different results with completely different winners. So that was it. If you have any questions, I think we still have plenty of time. You can also visit altinity.com or find me on LinkedIn if you have any more questions, or find me outside here. But yeah, first, I think we can get into the questions part. Oh, what do you prefer, local storage or network storage? Oh yes, that's a great question, because I personally, I don't run anything that needs this volume of storage. So whenever I need to, whenever I need to run something for myself, it's not of this scale. What I can say is that our customers usually decide based on their needs, which are many times actually security needs. So many times they choose to run their ClickHouse on their local servers, because this way they can get certified for different security certificates. So usually I see that this is the main reason of the choice. But also probably, I don't work closely with these people. As I said in the beginning, I work mostly on the UI. So there are probably people who could tell better in the company. And yes, if you want to get into it more deeply, we are happy to answer, our support team is happy to answer your question. Okay. And it seems like that's it. So thank you a lot for your attention. And oh, sorry. Oh, yeah. Thank you for the question. Yeah, that was really interesting to me when I first saw that. So we looked into that query, and the interesting thing there was that it included both a lot of computations and a lot of I/O. So what happened there is that, sorry? So what happened there is basically just, that was already outside of the range that ClickHouse could optimize. There we needed the operating system to step in and do its own cache. So even you could see that for most of this graph, we had pretty uniform results. But even this difference of the use case, even the query that we are going to use, is going to change what hardware we should possibly use. Okay. Was that clear? Yes. Okay. Okay, so thank you a lot for your attention, and enjoy your time here.